Welcome back to a new session of MOOC on Information Security. Today's topic is Transposition Ciphers. The objectives of this module are to define keyless and keyed transposition cipher, to discuss rail fence technique and columnar transposition, and to understand statistical attack and brute force attack possible on these ciphers. We have already mentioned that there are different techniques used in cryptography to secure our valuable data. Hiding the text data to make it secure is commonly referred to as encryption. In the introductory session, we learned that substitution methods and transposition methods are used for this purpose. Some uses keys for encryption and decryption, while some others are keyless methods. Transposition cipher. The commonly used substitution methods such as Caesar cipher, monoalphabetic cipher, Playfair cipher, Hill cipher, etc. were discussed previously. Here, the goal is to create some confusion so that a cryptanalyst or intruder cannot easily identify the original text and key from a ciphertext. Another method of scrambling with similar goal is transposition. It is an encryption technique in which the letters of message are rearranged instead of substituting it with some other letters of the same language. The transposition methods aim for diffusion or widely spreading the information from the message or key across the ciphertext. It is a method to rearrange the symbols of the message, which is also referred to as permutation. There are two methods to reorder the symbols to form the ciphertext, such as keyed and keyless transposition. Keyed and keyless transposition ciphers. In this cipher technique, the message is converted to ciphertext by either of two permutation techniques. In the first method, text is written into a table column by column and is then transmitted row by row. In the other method, text is written into a table row by row and is then transmitted column by column. The first method is popularly known as rail fence cipher and the second is known as columnar transposition. For example, we need to send the message, "Come and meet me." Arranging into table, we get in the first row first column C and the second row second column O and the first row third column M, like that, and the first row C, M, A, D, E, T, E, and in the second row O, E, N, M, E, M. Now, the message is sent row by row. So, the ciphertext is C, M, A, D, E, T, E, O, E, N, M, E, M. Here, the number of rows is 2 by default unless specified otherwise. Similarly, for the second method, that is B, we can arrange the same above message into table with 4 columns. In the first row, there will be come, the second ANDM, and the third row WTM, and the final row E. The data is then transmitted column by column as CAEE, ONE, MDT, EMM. Keyed transposition cipher. In this approach, rather than permuting all the symbols together, we divide the entire plain text into blocks of predetermined size and then permute each block independently. Suppose A wants to send a message to B. We have an attack. Both A and B agreed to had previously agreed over the block size as 5. So, the blocks would be as WEHAV, then EANAT, then TAACKX. The last letter X is a bogus character so as to complete the block size of 5. A and B using the following key for encryption and decryption. And rail fence technique. The rail fence cipher is a form of transposition cipher that gets its name from the way in which it is encoded. In the railfence cipher, the plain text is written downwards and diagonally on successive rails of an imaginary fence, then moving up when we get to the bottom. The message is then read off in rows. Columnar transposition. In a columnar transposition, the message is written out in rows of a fixed length and then read out again column by column. And the columns are chosen in some scrambled order. Both the width of the rows and the permutation of the columns are usually defined by a keyword. For example, the keyword zebras is of length 6, so the rows are of length 6. And the permutation is defined by the alphabetical order of the letters in the keyword. In this case, the order would be 6, 3, 2, 4, 1, 5. That is, if arranged alphabetically, A would be 1, B would be 2, E would be 3, R would be 4, S would be 5, and finally Z would be 6. In a regular columnar transposition cipher, any spare spaces are filled with nulls. In an irregular columnar transposition cipher, the spaces are left blank. Finally, the message is read off in columns in the order specified by the keyword. For example, suppose we use the keyword zebras and the message, "Come near the bridge, take your gun." In a regular columnar transposition, we write this into grid as follows. The positions will be 6, 3, 2, 4, 1, 5. The rows will be like COMENE. In the next row, ARTHEB. Next row, RIDGET. And the next row, AKEYOU. And the final row would be RGUN and QJ, providing two nulls Q and J. These letters can be randomly selected as they just fill out the incomplete columns and are not part of the message. The ciphertext is then read off as NWOQ, MTDEU, ORIKG, EHGYN, EBTUJ, CARAR. In the irregular case, the columns are not completed by nulls. Hence, in the final row, there will not be Q and J, and the final row will be RGUN. This results in the following ciphertext similar to the other one, but the last one will be without Q and J and the RAR only. To decipher it, the recipient has to work out the column length by dividing the message length by the key length. Then they can write the message out in columns again, then reorder the columns by reforming the keyword. In a variation, the message is blocked into segments that are the key length long, and to each segment the same permutation given by the key is applied. This is equivalent to a columnar transposition where the readout is by rows instead of columns. Double transposition. A single columnar transposition could be attacked by guessing possible column length. Writing the message out in its column may be in the wrong order as the key is not yet known, and then looking for various possibilities. Thus, to make it stronger, a double transposition was often used. This is simply a columnar transposition applied twice. The same key can be used for both transpositions, or two different keys can be used. As an example, we can take the result of the irregular columnar transposition in the previous section and perform a second encryption with a different keyword, stripe, STRIPE, which gives the permutation 5, 6, 4, 2, 3, 1. Hence, it can be encrypted as 5, 6, 4, 2, 3, 1 are the positions, and the first row will be NEEOMT, second DEUORI, third KGEHGY, and the next NEBTUC, and the last row will be AR. As before, this is read off column wise to give the cipher text. TIYCO, OHTRM, RGU EU, EBAND, KNAEEGER. If multiple messages of exactly the same length are encrypted using the same keys, they can be read simultaneously. This can lead to both recovery of the messages and to recovery of the keys. If you are interested, you can search in historical documents and find that during First World War, the German military used a double columnar transposition cipher, changing the keys infrequently. The system was regularly solved by the French, naming it UPCHI, who were typically able to quickly find the keys once they had intercepted a number of messages of the same length, which generally took only few days. However, the French success became widely known, and after a publication in Le Matin, the Germans changed to a new system on 18 November 1914. During Second World War, the double transposition cipher was used by Dutch resistance group, the French Maquis and the British Special Operations Executives (SOE), which was in charge of managing underground activities in Europe. It was also used by agents of the American Office of Strategic Services and as an emergency cipher for the German Army and Navy. Cryptanalysis. The double transposition cipher can be treated as a single transposition with a key as long as the product of the length of the two keys. In late 2013, a double transposition challenge regarded by its author as uncipherable was solved by George Lastry using a divide and conquer approach where each transposition was attacked individually. Detection and cryptanalysis. Since transposition does not affect the frequency of individual symbols, symbol transposition can be easily detected by the cryptanalyst by doing a frequency count. If the ciphertext exhibits a frequency distribution very similar to plain text, it is most likely a transposition. In general, transposition methods are vulnerable to anagramming, sliding pieces of a ciphertext around, then looking for sections that look like anagrams of words in English or whatever language the plain text was written in, and solving the anagrams. Once such anagrams have been found, they reveal information about the transposition pattern and can frequently be extended. Similar transpositions often suffer from the property that keys very close to the correct key will reveal long sections of legible plain text interspersed by gibberish. Consequently, such ciphers may be vulnerable to optimum seeking algorithms such as genetic algorithms and hill climbing algorithms. There are several specific methods for attacking messages encoded using a transposition cipher. These include non-plain text attack. Using non or guessed parts of the plain text, example names, places, dates, numbers, phrases, to assist in reverse engineering the likely order of columns used to carry out the transposition and or the likely topic of the plain text. Second one is brute force attack. If keys are derived from dictionary words or phrases from books or other publicly available sources, it may be possible to brute force the solution by attempting billions of possible words, word combinations and phrases as keys. The third is depth attack. If two or more messages of the same length are encoded with the same keys, the messages can be aligned and anagrammed until the messages show meaningful text in the same places without needing to know the transposition steps that have taken place. The fourth one is statistical attack. Statistics about the frequency of 2-letter, 3-letter, etc. combinations in a language can be used to inform a scoring function in an algorithm that gradually reverses possible transpositions based on which changes would produce the most likely combinations. For example, the two-letter pair QU is more common than QT in English text. So, a cryptanalyst will attempt transpositions that place QU together. A detailed description of the cryptanalysis of a German transposition cipher can be found in Chapter 7 of Herbert Yardley's The American Black Chamber. A cipher used by the Zodiac killer called Z340, organized into triangular sections with the substitution of 63 different symbols for the letters and diagonal night move transposition, remained unsolved for over 51 years, until an international team of private citizens cracked it on December 5, 2020 using specialized software. Encipherment and decipherment complexity. This cipher involves no additional work beyond arranging the letters and reading them off again. Therefore, the algorithm requires a constant amount of work per character, and the time needed to apply algorithm is proportional to the length of the message. But we should consider the space required to store the ciphertext. The other ciphers so far we have considered required only a constant amount of space, but columnar transpositions require space to store all the characters of the message. Hence, the space is not constant. And the output text cannot be produced if the entire message is not read, because all the characters in first column should be done before starting the second. Thus, the delay also depends on the length of the message instead of the constant delay in other algorithms. Vernam cipher. A subset of Vernam cipher is called a one-time pad because it is implemented using a random set of non-repeating characters as an input ciphertext. Once the input ciphertext is used for transposition, it is never used for any other message. The length of the ciphertext should be equal to the plain text. Working of algorithm. Step 1. Arrange all the characters in the plain text as numbers, that is A equal to 1, B equal to 2, etc., Z equal to 26. Step 2. Repeat the same procedure for all characters of the input ciphertext. In step 3, add each number corresponding to the plain text characters to the corresponding input ciphertext character number. Step 4. If the sum of the number is greater than 26, subtract 26 from it. Step 5. Translate each number of the sum into a corresponding character. Step 6. The output of step 5 will be the ciphertext. For example, plain text is welcome. The key is compute. Now, according to our encryption algorithm, we assign a number to each character of our plain text and key. The plain text is WELCOME. The corresponding numbers are 23, 5, 12, 3, 15, 13 and 5. The key is compute. The corresponding numbers are 3, 15, 13, 16, 22, 20 and 5. Now, add the number of plain text and key, and after doing the addition and subtraction operation if required, we will get the corresponding ciphertext character number. The sum will be 26, 20, 25, 19, 37, 33 and 10. In this case, there are two numbers which are greater than 26. So, we have to subtract 26 from them, and after applying the subtraction operation, the new ciphertext character numbers are as follows: 26, 20, 25, 19, 11, 7 and 10. New ciphertext is produced after getting the corresponding character from the number. Hence, the ciphertext will be Z, T, Y, S, K, G, J. In Vernam cipher, once the input ciphertext is used, it will never be used for any other message. Hence, it is suitable only for short messages. So, in this module, we have discussed the important transposition ciphers and the way they are forming the ciphertext. Hope the session was useful for you. See you next time. Bye.